Hello students, today in this class we will learn about the design of rectangular tanks. In the previous class we have completed the design of circular tanks with two conditions. One is the base slab is rigid or whether it is flexible. So these two are the conditions for which we have designed. So today we will study about the design of rectangular tanks. Again we have two methods here, approximate analysis and exact analysis based on the elastic theory. Means we are going to use IS code here, IS 3370 we are going to use for the design. In the first class, in the present class, we will study about the approximate method, and later on we will study with the IS code method. So some formulas and conditions are there in this. So we'll go through them and then we'll take up an example. The approximate method. For the design by approximate method, the rectangular tank may be divided into two categories. So this is based on mainly the ratio of length to breadth. Whether the length to breadth is less than 2 or whether it is greater than 2, based on that again we have two categories. So first is length to breadth ratio less than 2, where L is the length, B is the width, and H is the height in this particular chapter we are using. So H is the total height from the inside measurements. Here tank walls are designed as continuous frames with, that is rigid one, subjected to triangular load. So here water pressure will be acting on the walls. So this will be considered as a triangular load, and such a bending is assumed to take place from the top to a height of h height, that is h by 4 or 1 meter above the base slab. Means this triangular load will be acting from the base to certain height. So that height will be total capital H by 4 or maybe 1 meter above the base slab. So whichever is more, whichever is higher, that we are going to consider in the design. For the bottom height H, that is the triangular portion what we are going to consider where the cantilever action takes place. This is for the cantilever action. So from the bottom height H, the bending is assumed to act in a vertical plane as a cantilever and subjected to triangular load as shown in this figure D, B, C. So this is the triangular portion here, DBC, and this D1, B, and C. Having zero intensity at D1 here and WH at the base, that is the water pressure. WH, intensity of that is unit weight of water into height, total height here H. Completely it is a triangular portion. This is a water pressure applied over this vertical wall of the water tank. At the top it will be 0 and at the top it will be maximum, that is W into H. But when we are considering the cantilever action in this particular design, that will be for a height of H, small h, which is equal to H by 4 or 1 meter. So we'll consider this triangle and this much portion will be considered for the cantilever action, and remaining will be as it is we are going to design with the moment distribution methods. So please go through these two figures. These are important. Calculate the height and the intensity as well as to get the to obtain the fixed end moments at the ends of these corners or the walls. So here AB is a long wall, DC is a long wall, PC and AD are the short walls. Here PB square by 12 and here is the PL square by 12. These are the fixed end moments obtained at A and similarly at B, C and D. For horizontal bending, the maximum horizontal force per unit weight at D is taken equal to P is equal to W into H minus H. That is the remaining portion here. So this is the distance we are considering, or this height we are going to considering, remaining height, that is total H minus small h we are going to consider, and for this horizontal pressure will be considered, and we are going to design the wall, this particular section of the wall. The panels are assumed to be fixed at the supports, and fixed end moments are calculated. The final moments are then computed by moment distribution method. So you are already learned the moment distribution method. It is one of the simple method to obtain the moments at the ends and at the midspan. So if P is the water pressure at D, and the fixed end moments for long slab AB will be PL square by 12, while fixed end moment for the short slab, that is AD, will be PB square by 12. So you can see in the figure also for AD it is PB. This is a short wall, right? So it is B, here is the L. So this moment will be PL square by 12 and this moment will be PB square by 12. One is clockwise, another is anti-clockwise here. After finding the moment, fixed end moments, this PL square by 12 and PB square by 12, that is MF, I am going to indicate here, or sometimes M. At A, moment at center of AB can be calculated. So these are the fixed end moments at the corners, and with the help of these I can calculate the moment at the ends. So that is by AB central span moment AB is equal to PL square by 8 minus MF. For short span it is PB square by 8 minus MF. So what we need to calculate initially is this PL square by 12 and PL square by 8, PB square by 12 and PB square by 8. These four things are to be calculated. Then need to calculate MF by fixed this moment distribution method. Then if I deduct PL square by 8 minus MF or PB square by 8 minus MF, that will give me central span moment for the span of AB or maybe shorter span AD. But in the absence of moment distribution method, the bending moment may be computed by the following approximate expressions, that is PB square by 16, PB square by 12 for center span. So what we have used here is PL square by 8 minus MF. So instead of that, I can go for use of this PB square by 16 and PB square by 12. So here is the central span moment. What I obtain here is PB square by 16 for end span of PB square by 12, and similarly for the long wall also I can obtain this. Already I have this PL square by 12, so I can obtain this as PB square by 16, PL square by 16. Similarly for the longer span, this is for the shorter span here. Similarly I can obtain this for the longer span as PL square by 16. So this will be produced, this will produce the tension on the outer face, means we need to provide the reinforcements at the outer face here, and for the end span movements, water face means inner side of the walls, we need to provide the reinforcement. So we must remember these two things in the detailing of the reinforcements. In addition to the bending moment, the wall are subjected to direct tension. Not only the bending moments are there, it will be, the walls will be subjected to direct tension also. So on the longer wall, PL, or I will take it as TL, or for the shorter wall, I will consider this as PB or maybe TB, or let's say TS. Sometimes I may use this direct tension as P or maybe T, right? So here PL is equal to W, that is unit weight of water, into H minus H into B by 2. And for short wall, PB is equal to W into H minus H into L by 2. So for short wall, it is L by 2. For long wall, it will be B by 2. We need to remember this. How it is B by 2 or L by 2, we will see this from the figure here. So this is the tensile force acting in this direction for the longer wall, right? So in this direction, if it is acting, means it is perpendicular to this wall, that is B. So this will be B by 2. Again, for the short wall, it is acting in this direction or maybe in this direction. So this is perpendicular to this L, longer wall. So this will be PL by 2. For the shorter wall, I am going to consider L by 2. For longer wall, I will be considering B by 2. So that's how we can remember these two formulas. So now we will take up an example. Example 1, an open rectangular tank of dimensions 4 meter width and 6 meter length, and depth is 3 meters, rests on firm ground. So we need to design the water tank using M20 grade of concrete and let's say Fe4 on 5 steel. So first I have M20 grade of concrete. So with the properties sigma CB is 7 Newton per mm square. So I can find the modular ratio M. It is 13. We have already calculated these in the initial steps also, or else you can obtain it from the working stress method. And sigma st, it is these values are available in IS 456 as well as 3370 part 3 part 2. So sigma st is equal to 115 Newton per mm square, and K it is 0.442, J equal to 0.853, and R equal to 1.32. In the second step, I will determine the horizontal bending. So I need to obtain now what is the ratio, whether this L by B ratio is greater than 2 or less than 2. I need to check now. So first condition it is L by 2 is less than 2, and I need to calculate what is H by 4. So H by 4 is small h, it is 3 by 4, is less than 1, or it is 1 meter, whichever is more. So I will consider this because it is more than 1. It is less than 1 and it is 1 here, so h is equal to 1 meter. So total height is 3 meter, out of which this is 1 meter. This small triangular portion, that is the cantilever action portion, is 1 meter, and remaining h minus h value will be 2 meters. So bottom 1 meter will bend as a cantilever, vertical cantilever, and top 2 meter height of walls will bend horizontally. So water pressure I will calculate now at point D. Here is a point D at this particular point. So water pressure at the top of this H, or up to at the height of 1 meter from the base, it is P pressure is equal to W into H minus H. So 9.81 is the unit weight. I can use this as 9.8 or 9.81 rounding off. So H minus H, it is 3 minus 1. So it will be 19.62 kilonewton meter, or converting this into kilo, that is into 1000, so it will be 19,620 Newton meter. So now I will calculate the fixed end moments for short wall and long walls. So for the long wall it is PL square by 12, so this will be 3P, and for the short walls fixed end moments will be PB square by 12, so that will be 4 by 3 P Newton meters. So once I calculate this PL square by 12 and PB square by 12, I can directly calculate PL square by 8 and PB square by 8, which will be helping us to obtain the moment at center span. So before that, I can go for fixed end moment calculation using this moment distribution method. So consider the quarter span of the frame as shown in the figure. So going back to the figure, okay, here is the figure. So I'll consider this quarter span, this much portion. So E is the center of this AB and F is center of AD. So this I will consider this frame, and I will calculate the fixed end moments, this PB square by 12 and PL square by 12. So you can use this moment distribution method in whatever way we have used, you have used in your previous classes of structural analysis, and obtain the fixed and obtain the moments. So I will use here in the tabular format, taking clockwise moments as positive and anti-clockwise moments as negative. The fixed end moments MAF for long span will be 3P, what we have calculated here, and for the short span it is 4 by 3P, right? So this will be positive and this will be negative, minus 4 by P, 4 by 3P. We can observe this from the figure also. So member stiffness, relative stiffness, and distribution factor. So long wall AE, it is 2EI by L. Again for short wall also it is 2EI by L because both ends are fixed. So 2EI by L is 6, so it is 1/3 EI, 1 by 3 EI, and similarly it is 1 by 2. 2 by 4 it is, right? L is 4 meters, so 2 EI by 4 it is 1 by 2 EI. So it is 1 by 3 EI and 1 by 2 EI. into this total 1 by 3 and 1 by 2. I will consider this for the relative stiffness. 1 by 3 into 6, that is 2 into 3, it is 6. So relative stiffness is 2 here for long wall, and for short wall 1 by 2 into 6, it is 3. So distribution factor will be calculated here. It is relative stiffness divided by summation of the relative stiffness, that is 2 plus 3, it is 5. So 2 divided by 5, it is 0.4, and 3 divided by 5, it is 0.6. So I will rewrite the table here to calculate the final moments MF. So joint is A, member AE and AF. Distribution factor we have calculated 0.4 and 0.6, and fixed end moments we have calculated plus 3p and minus 4 by 3p, and balancing moment is this plus this by 2. So it is minus 2 by 3p, and here it is this into this, it is this into this, it is 2 by 3p, and it is minus p. So this will be balancing moment. I will calculate here. It is minus 2 by 3p, and it is minus p, and final moment will be 7 by 3p, and here it is again minus 7 by 3p. This plus this, these two calculations. So hence total moment or support moment MF is equal to 7 by 3p. So you can follow this method, or whatever method you have followed to calculate the friction moment, and use that. But finally what we need is the moment at the support. So here I have obtained this as 7 by 3p. So P is 1,96,200 it is, or it is 196.2 kilonewton meter. So I will obtain now MF is equal to 7 by 3 into this. So MF is equal to 45,740 Newton meter per meter span. So now I will obtain the center span moments, bending moments. So for long span it is PL square by 8 minus MF, and for the short span it is PB square by 8 minus MF. So substituting the values of P, L and MF, I will obtain here as 42,400 and 460 Newton meter per meter span. And similarly for short span central bending moment, bending moment at center of the short span will be minus 6,540 Newton meter per meter span. So these two moments will be acting at the center span, but for the longer span this will be acting outer face, and for the this shorter span tension will be acting in the inner phase, that is water phase. So now design moment we have obtained, that is MF, it is 45,740. Initially we have calculated this, right? So here it is 45,740. This is the design moment. So we will use this design moment. This is another method, so don't worry about this. So once we have this design bending moment 45,740 Newton meter per meter span, we are going to design the section for that moment. So D is equal to M divided by R into D. B, so B is 1000. This is Newton meter, so I have converted that meter into mm. So it is 45,740 Newton mm into 1000. So it is 1.32 divided into 1000. So I will obtain D is equal to 185 mm. So let's consider total depth is equal to 220 mm. So effective depth is equal to 220 minus 35 equal to 185 mm, where I am considering 35 mm cover. So now I will calculate the pull, that is direct tension along the long wall and the short wall. So TL, or it is PL, is equal to PB by 2. So it is 19,600. I have rounded off that. I have neglected this, means I have considered this as 9.8 kilonewton per meter cube density of water. So it is 19,600 into 4. B is 4 divided by 2. So it is 39,200 Newton. It is the direct tension on long wall. Similarly, for the short wall, it is PL by 2. So it is P into L is 6 divided by 2. It is 58,800 Newton. And we have cantilever moment also at the base, from the base at a height of 1 meter. So it is WH into H square by 6. So it is 9,800 into 3 into 1 square by 6. So it will be 4,900 Newton meters. So this will be causing tension on the water face. So once we obtain the moments and these direct tensions on the short wall and long wall, we will calculate the reinforcement at the corners and at the center span. So AST at long wall corners will be, it is for the long wall corners, so it will be MF or M minus TL or PL into X divided by sigma ST into J into D plus TL divided by sigma ST. So here what is X? X is the distance measured from the center of this wall to the reinforcement. So reinforcements are placed here, and this is the central span, or it is the center of the wall, and from here to here it is the effective depth. So this is the effective depth minus capital D by 2 or T by 2. Let's say this is the total D. So D by 2 means this. So effective depth minus D by 2 will give us X value. So X is equal to effective depth minus D by 2 will give me X is equal to 75 mm. So substituting this X value in this equation for the AST calculation for long wall, it is 2700 mm square per meter height. So these reinforcements are provided in horizontal direction. They are not vertical reinforcement. These are horizontal reinforcement. So using 20 mm dia bars, area of steel, one steel bar is 314 mm square. So spacing is equal to 314 divided by 2700 into 1000. So spacing is equal to 116 mm. So hence provide 20 mm dia bars at a spacing of 110 mm center to center. So these are the reinforcements provided at the corners. So these reinforcements will be continued at the central span also. So this reinforcement is provided at inner face at near to the corner or at corner and at a height of 1 meter above the base slab. So these are the reinforcements provided above the 1 meter height, not at the 1 meter height above the from the base slab. So that is for the above the base slab of 1 meter span, we will consider that as an this cantilever action. So reinforcement will be provided separately for that. So this is for the movement calculated above the 1 meter height above the base slab. So for other heights, as the pressure, water pressure increases with the height, so we may increase the spacing, means the spacing will be varied now. So here let's say I am providing 110 mm center to center at 1 meter span above the base. I may be increasing this to 220 at 2 meter span above the base. So that's how I can increase the spacing. So reinforcement at middle span. I have calculated the reinforcement at the corners. Now I will calculate the reinforcement at the middle span of the long wall. So moment I have calculated 42,460 Newton meter initially. So we'll go back to that calculation and we'll see 4,200. Okay, here is the central span moment, right? So this is the central span moment for long wall and similarly for the short wall also there, right? Okay, we have this moment, and for that central span moment, that is at the middle of the long wall, it is 42,460 Newton meter, and pull, that is 39,200 Newton, and X distance is 75 mm. Again, substituting in the AST equation formula, I will obtain AST is equal to 2505 mm square per meter height. So using again 20 mm dia bars, as this value is similar to the steel provided at the corner. So you can see here it is 2700 and here it is 2500. So I can provide same spacing and same reinforced bars here. So provide 20 mm diameter bar at a spacing of 110 mm center to center. Bend half the bars provided at the ends towards at a distance of L by 4, that is 1.5 meter from the ends, means from the corner up to the 1.5 meters. Take the straight bars and then bend these bars towards the outer side, because outer side will be tension. So these bars will be taken outer face to the outer face. So provide additional 20 mm bars at 220 mm center to center, means when I am placing this or when I am providing these 110 mm bars for the central span, so alternate bars I am going to extend them beyond this L by 4 distance, that is 1.5 meter distance. So spacing will be increased now. So 110 is the spacing, but when I'm alternate bars are being taken straight at the outer wall, then spacing is going to increase double. So it is 220 mm center to center. So this is about the reinforcements required for the long walls. Similarly, we can calculate the reinforcement required for the short walls. So students, remaining calculations we will take in next class. So before that, again go through these calculations once again, and next we are going to study about the reinforcements for the short walls and reinforcement to be provided for the cantilever action for a height of 1 meter from the base slab. Thank you.